Okay. Right. Okay, so here we have a case about a steel ball with a radius r is suspended in air. Yeah, the ball temperature is TB, and then the air temperature is TU. So you imagine that we have a ball, and then this one is the temperature is TB, so it is like a hot metal ball, for example, and the temperature around the air around the ball is actually T udara, yeah. So for example, this is T bola and this one is T udara. Okay, and then because the TB is larger than TU, so what happened is, what can you guess? Of course, that would be some heat transfer from the TB will transfer into the TU, right? So it will transfer into the TU. Okay, and then so the from the surface of the steel ball to the air by conduction. And the difference of TB and TU is not too large. Wait. I think, yeah. This one, let me just copy. This is the number 2, is it? I think I need to add one more. This is number 3. I think this is the wrong problem. Yeah, give me 1 second. Sorry for that. Okay. Okay, let's have a look. This is from 3 years ago, so I think this would do the job. It's slightly different, yeah, but anyway. Okay, so we have a steel ball with a radius of r, and then in the like still air or moving air, and then the ball temperature is TB. So this is the ball. Let's say this is the TB. Sorry, my writing is not really good. I forgot to bring the Wacom, yeah. And then, okay, so because while the air temperature is the TU or T air, as the TB is larger than the T air or the TU, or let's say just this using air, the heat conduction will occur from the surface of the steel to the air. So because this one is hotter, the TB is larger than T air. Of course, if you have a hot ball, if you have a hot ball, and then of course the heat transfer will occur from the surface of the ball, of course, to the air, right? So here that would be a heat conduction occurs from the surface of the steel ball to the air. So the key is first there's conduction. Okay, because of the heat conduction, the temperature of the steel ball would be equal to the temperature of the air. Yeah, so this one around here would be the T air. So imagine if you have if you boil an egg, okay, you boil an egg to make a boiled egg, yeah, telur rebus, and after that, after you heat it, you put it into after it's boiled, and then like, for example, 15 minutes, so everything is like in a boiling temperature, for example, 100 degrees Celsius. And then we immersing into a cold water, right? When we immersing into the cold water, if you hold the surface would be similar to the temperature of the water at that for that moment. But after a while, it will gradually increase. Okay, okay. So here, please derive the differential equation of the temperature profile in the steel ball from the steel energy balance and write down the boundary condition applied. Okay, so now the other key is actually the shell energy balance. So we have to make the shell energy balance, and then later on we're going to do the integration, but in a sphere. Okay, so there are few ways to do this, but what we can do, we can make the shell balance is a function of R. So start from the center and then to the increase. Okay, and then we can also write the boundary condition applied. Or maybe from here, can you guess the boundary condition applied? So the boundary condition, if I want to check here, the first one would be the ball temperature is TB when the ball temperature is TB when in the beginning. Okay, and here, so the ball temperature is TB, okay, and then the air temperature is TR. Okay, so this phenomena is actually an unsteady state. Yeah. Oops, sorry. It is unsteady. Why? Because in the beginning, like in the case of unsteady, in the case of boiling egg, at the beginning, the egg is very, very hot. Yeah, it has been boiled, and then you immersing in the here. Yeah, okay. So here, and then when we immerse it in the cold water, of course, the temperature will changing inside the steel ball or inside the egg. It will changing. So because the temperature will change because it's immersing in the cold water, or in this case, immersing in the air. So what happened? That would be a temperature gradient. Okay. Okay, so the first one, so the ball temperature, the beginning is TB. So this actually tells you that at T equal to 0 in the beginning, the temperature is TB. Okay, so this is one boundary condition. Another one, the boundary condition that we can see that the temperature after it immersed, the temperature of the steel ball surface would be equal to the temperature of the air. So the surface, which is the T at R equal to the surface means on the radius, right? So on the R, that's equal to temperature of the air. Yeah. And then there would be one more, would be one more boundary condition, and this is the second one, and there would be another one later on. We'll see in a minute. Okay, so, and then for the shell energy balance, if we are using plate, yeah, and then the shell energy balance would be some like a thin plate. If we're using a cylinder, for example, the energy balance would be like a thin shell. For the sphere, the energy balance, the shell would be looks like a shell, cangkang bola, yeah, like a steel shell. Right. Okay. So again, we see the shell energy balance, this one. So because it's only considered the conduction, so what we need to do is just to look at the molecular transport. Yeah. So the convective, the energy, the work done, energy production is actually immersed. Yeah. It's actually we neglect it because there's no energy production, there's no work, there is no so we're only using the molecular transport or the conduction. Okay, so this is the result. So the first one, so if this is the sphere, we can make a thin shell, looks like a sphere, cangkang bola ya, seperti kulit bola, with the dr. And then again, we can write the Q in over here, which is QR. The Q is this is the one is the capital one, which is the heat flux multiplied with the area. Okay, heat flux with the area. So here the Q is first the QR, and then the area is the area of the surface area of a sphere, ya, luas permukaan bola, which is 4 pi r square. Okay, and the Q out also QR plus delta R. We can write it here also would be like that. Okay, and because of that, there would be some accumulation. What does it mean? Because it is an unsteady state. The accumulation can be the heat is increased or the heat is decreased. Why is decreased? Because it's transferred from the steel ball into the air. Okay, why is it decreased? Because, for example, in the case of the egg, the heat in the egg is transferred into the cold water. Okay, so after a while, it can be cooled down, and the water maybe would be a little bit increased. But for this case, the air is large enough, yeah. So the transfer over here doesn't increase the temperature of the TU, yeah. If the TU is very small, or sorry, if the space in near the, let's say the space near the ball is really small, like if you put the egg into a glass of like a glass, of course the temperature will heat it up. So that means the TU will increase with time. Okay, so this one, or the T air, sorry, I'll just put the T air would be increased. But for this case, the boundary condition, the T air would be just still the T air, doesn't change. Okay. Okay, so now the accumulation. What's the accumulation? The accumulation is the MCP dou T over dou T. Yeah, so the rate, the increasing rate of the temperature. So M, which is the rho multiplied with the volume, and then the CP, the heat capacity, and then the increasing temperature over dou T, the rate of temperature. So you can substitute over here, and then you put the volume of the shell. How do you write the volume of the shell? Rho V r square, rho pi r square, multiply with the thickness. Okay. So the shell energy balance would look like this: Q in minus Q out plus Q generation equal to Q accumulation. There's no Q generation over here, so we can just put the QR over here, and then you have to make sure that R square is different in the in and also in the out. So when you divide it both sides, you divide it with only with 4 pi delta R. Okay, so over here you end up with you will end up with the differentiation of the here, yeah. So and then you also substitute, you also put the QR, you change it with the Fourier flows, yeah, which the QR would be minus K dou T over dou R. Yeah, so this one is actually the Fourier flow. Okay, so there you go. You got both sides over here. So you have two differentiations. So first one dou T over dou R and dou over dou R of R K R square K dou T over R. And then we can do one integration over here. So this become, yeah, we can divide both sides with 1 over with R squared. So over here there's 1 over R dou something, yeah. And then after that you can make it just to make sure, K, put it over here. And this one is the thermal diffusivity. Yeah? So, and then this one is actually 1 over alpha, where alpha is called the thermal diffusivity, which is K over rho Cp. Yeah, so this one is 1 over alpha. Okay, for the boundary condition for the syarat batas, so at R equal to 0 over here, the temperature is equal to TB. Okay, and when R equal to R in the over here, the temperature equal to R, air, sorry, the udara, T udara. And then when T equal to 0, all the temperature would be equal to the TB or T bola. Yeah, so that's it. And then when we if you want to calculate it, this one, we will we need to do using MATLAB or using FlexPDE. Okay, yeah, so that is one question. Maybe any questions or any questions? Okay, is it quite understandable? All right. Anyway, this is recorded anyway, so we can yeah, we can check. You can check this later. Okay. I think I also need to show you. I just have a work done with the, but this one is quite. It can be like a final project. So let me share a little bit to you. This has become like one of the final project with the students, with the kakak kelas, yeah, yes, especially during the COVID, because they can't do the experiment. Give me 1 second. Okay, so for example, this one. So this one is the one of the is one of the simulation that we did with Dion, yeah, and Naufal 2018, yeah. Okay, so we want to do, so this become the simulations of like a hybrid coal, and then the hybrid coal is we treat it as like a sphere, like a ball, and we want to know how is the temperature profiles, and then how is the reaction profiles, yeah. So in this case, it's quite long introduction, the methodology, and then so this one is the anyway. So this tells you that the conversion of reaction is a function of temperature, and then the temperature is a function of the distance and time. Yeah, so think about when you, because in a solid, if you have a different temperature, of course solid will have different temperature because of those unsteady things, and then with different temperature, your conversion because of reaction rate is different as well. So they incorporated those two, and then with also with the, yeah, the like this one, the heat transfer, yeah. So this is the heat transfer, looks like this, and then the lambda is actually with the alpha, yeah, 1 over alpha, and then also we calculate the thermal diffusivity in this case, rho Cp also, yeah, we modeled with the temperature because it's changing with the temperature, and then we calculated like using okay, like this one. Okay, so at least with the modeling, you can see if you have a steel ball, if you have a ball, it's called the hybrid coal, and then the temperature is actually at certain time and certain position, they have a different temperature, right? So this tells you the time, this tells you the position, and then this is the temperature. So you can see that the temperature would be quite increased, yeah, it would be very cold, and in the beginning 0, and then as the temperature increase, at the time increase, the temperature also increase, but then you can see that on the surface it become hotter, yeah, it become quite hotter compared to this one. So the blue one is the cold one, the yellow one is the hotter one, yeah, would be like this. And this also in the 2-dimension, you'll see that the temperature, so it actually would take some time. If, for example, if we set the temperature outside is 300 degrees Celsius, when we have a different radius, when we have one radius in the center, the blue one, in the center of the ball, and also in the middle, and also in the surface, they have different temperature. Okay, so this actually tells you about we can model any shape or any type of phenomena. For example, for this one is the unsteady. Okay, and then for example, you can but this also has been validated with the data. Yeah, so of course we need to validate it with the some data, the temperature, and then for example, I can show you too. So here, from here we can see the Rendement massa, which is the yield of the reaction, because the reaction is a function of the kinetics, and the kinetic is function of temperature. Yeah, so this is like a kind of advanced way of transfer phenomena where you combine both the temperature difference, the heat transfer, and also the reaction, and then combine them together. All right, so this one was presented in the STKSR, and then is processed into a journal paper. All right, maybe before I change the topics into equation of energy, maybe any questions? No? Okay, I think we can discuss it hopefully next week, yeah, in the class. I hope I should be getting better. Okay, now you can open the, wait, where is it? You can open the EduNext. In the EduNext is week 8, I think, about the equation of change. Okay, we can open, see the equation of change. Mana ya? Okay, so for the equation of change or equation of energy is actually quite similar with the momentum transfer. Again, the rate increase of kinetics and thermal energy is defined as the rate of kinetic energy and internal energy, yeah, the net rate of kinetic and internal addition by convection, and also addition by molecular conduction, and then rate work done on the system, and also rate of work done on the system by external forces, for example, by gravity. So let's have a look about the equation of energy. What does it mean with the equation of energy? So if this is the Cartesian diagram, and then we put like a space, yeah, like a space coordinate with the dx, dz, and also dy, for example. And then we break down the kinetic energy and the internal energy. This is the kinetic energy, and this is the internal energy. And this one is the E, which is conduction, convection, and so on. And then we can divide it both sides with the delta x, delta y, delta z, and then we come up with this differential equation, which is all this accumulation equal to the changing in the energy because of conduction and so on, yeah, conduction or convection and so on, and plus the gravity if it is easy, yeah. So this is called the equation of energy. Okay. So the rate of increase energy per unit is equal to the rate of energy addition by convective transport. If we break down the E, yeah, so if we break down the E, that become the convective. This one is become the conduction. This is the divergent, dou over dou of the space, the rate of work, the work done, and also work done by external forces. But the one that we often use is the heat conduction or convective, yeah. So, and then you can open for the appendix, you can use the appendix B, appendix B2, which is the Fourier's law of heat conduction. This is the Cartesian diagram. This is the cylindrical coordinate, yeah, for the QR is minus K dr dt dr, but for Q theta, there's like 1 over r, just make sure you know that. And this is in the spherical coordinate, yeah, the QR, Q theta, and also the C, yeah. Yeah, similar with the momentum. If the momentum is tau yx, for example, this is the energy. And then another one in the appendix that you need to know is the appendix B8, the equation of energy. Again, for example, in the momentum, you have appendix B5 and B6, yeah? The equation of momentum related to the tau, and also equation momentum related to the velocity. For the equation energy, you have appendix B8 and also B9. The equation of energy in the term of Q, and also in the term of the temperature, yeah. So this one in the term of the Q, which is, for example, for the Cartesian, rho Cp dou T over dou T like this, equal to dou Qx over dou X, then and so on. And then you can change this Q with the Fourier's law minus K dou T over dou T over dou X, yeah. And this is the cylindrical coordinate, and this is the spherical coordinate. Just make sure you know which one to choose. The next one is the B9, the equation of energy for here. This is when the constant rho and K, then you're gonna see that this one is a function of a temperature. Okay, so have a look again about Cartesian coordinate, cylindrical coordinate, and spherical coordinate, yeah? But mostly we use a Cartesian and cylindrical coordinate as well. Okay, and then this just to remember you to remind about the dimensionless number. We may use the Reynolds number, which is the initial force multiplied by viscous force. Freud number, we use this in the momentum transfer, I think, so regarding the tank, yeah, with the vortex in the tanks, comparison between inertial force and gravity force. And also, if you remember, this one is we use in natural convection, a Grashof number, which is a buoyant force. Rho G is which is rho is function of temperature, and divided by inertial force. Okay, so let's say you can open the book, or you can use you can check the ebook over here. let's try redo the problem. For example, for convection for a fully laminar flow in the tube. So how to make the temperature profiles of the fully laminar flow in the tube. Okay, so here we assume okay, so let's say we assume so this is one is similar with the convection that we discussed like last week, yeah, about we have a tube, maybe let's say vertical. Okay, and then this at certain time, at certain points, it is heated up, for example. Yeah, and then we want to know the temperature profile inside the cylindrical pipe, fluid inside cylindrical pipe, which is the outside is heated up or cooled down. Yeah. So the first one, you can use the equation of continuity. Again, we still use continuity, and you see that the equation of continuity automatically satisfied of the postulate. The second one, with the equation of motion, if you look at the appendix B, maybe B5 or 6, yeah, 6 maybe, you will end up with this one. Yeah, the equation of motion will give the velocity distribution or the parabolic velocity profile. I think you know already the parabolic velocity profile. Okay, and the last one from the equation energy or equation of B8 or B9, you can get the convective heat transport in the term of the this one is the convective one on the left side, and the over here the second one is in the conduction in the to R direction to the R direction. This is conduction to the Z direction, and this one, if you remember, is called the viscous dissipating heating term. Yeah, on the right side. Okay, so let's have a full practice just to check. So let's say, for example, this is the equation of continuity. Again, we have the fluid flowing, and then we have a heat flux on the surface like this. So the equation continues to tell you if this is the equation of continuity, though rho over dou T is 0 because it's steady. For example, though we don't have v to the R, we don't have v to the theta, and this actually tells you dou over dou Z of rho v Z is equal to 0. Yeah, this yeah, that's why the equation of continuity satisfies the equation. Another one, the equation of energy. For the equation of energy, we use B2, yeah, or in this case, I'm using B8 also is okay, or B9 also is okay. But in this case, I use B8. So here we have the cylindrical coordinate. I'm choosing the cylindrical coordinate, and then choose because it's steady. So delete this one. We don't have VR, we don't have V theta, we don't have dou T over dou Z. Yeah, we also don't have dou T over dou Z as well. So sorry, we do have dou T over dou Z, so I have to delete this one. So rho Cp Vz dou T dou Z, and then we have Q to the R over here. We don't have K theta, we don't have Kz over Z. Sorry. Yeah, this one. And then sorry, we do have this is the conduction. This is conduction to the Z direction. This is conduction to the R direction. Yeah. And then over here is called the viscous dissipation. So we don't have any changing in P. P means pressure, so we don't have that. We don't have that. So we end up with viscous dissipation term, though Phi, this one, and then this one also usually neglected, except for a system with a very large velocity gradients. Yeah, this also neglected. This also neglected because we don't have changing in pressure. So we end up with this one. We end up this equation, rho Cp Vz dt equal to 1 or RQR dou Kz over Qz over rho z. And then you can change QR equal to this one, QC equal to this one. Give me 1 second. Okay, so you get similar results. You will get similar results first using shell energy balance, and you also using this one, using the equation of energy. Okay, or this one, if you want to use the temperature, the B9, then you can end up almost, yeah, you get also rho Cp Vz over dou T over dou Z, and this one is the convection, this one is the convection. So any ways, yeah, any routes should do, you can use the shell energy balance or using this one. But usually in the exam problems, it will be defined. Should you use shell balance or should you use should you use this one, the equation? Okay, this one I just copy back with the slides, yeah, from Pak Mubiar and Pak Arse, which is similar, so we can skip that. Okay, maybe for this case, any questions or not? Okay, let's keep going, yeah. Okay, and then second one, let's have a look also with the tangential flow with anodes with the viscous heat generation. This topics also we have discussed it before last week with the shell energy balance, but now we're using the equation of energy, equation of change, yeah. Similar, if you remember, the konduksi panas dengan sumber viskos panas, yeah. And then we treated the this annulus like a two plates. Okay, with the angular velocity of omega. So here, yeah, so tangential flow of anodes with the viscous heat generation. You can use the energy equation with the B9, I think, yeah. So we can delete this one because this is unsteady. Vr is 0. We have V theta, but dou T over dou theta is also 0. It doesn't spin it much, ya, or memutarnya melambat atau menjadi cepat, ya, tidak, ya. And then we don't have Vz. This is for the tangential one. We don't have this case, so here is the energy equation. Okay, this is the viscous dissipation if you want to check the viscous dissipation, but we also neglected. We can't neglect this one because it's the dissipasi panas, yeah. So this is the equation for viscous dissipation in the book, and then is equal to this one. And then we multiply with this one. Okay, so anyway, so from energy equation, you end up with this one, and then we can check with the equation of change. And if you remember our calculation before, this is gonna be the phi theta, yeah, from the momentum balance. So we end up with similar equation. Okay, so now the boundary condition, we know that T equal to TB at R equal to R, and then the T equal to T0 at equal to KR, which is in the beginning. So yeah, okay, and the K. Okay, and then if you remember, we also can change into dimensionless form. So with the zeta and also yeah, over here. And again, we always use theta as a dimensionless number of the temperature. yeah, the temp, which is the T minus T0 minus the difference of the temperature, yeah, with this boundary condition, with also with N, which is N is the sum of the, this is a number, yeah, mu, the angular velocity, r squared, k, the ratio between the inner radius to the outer radius, and so on. Okay, so then using as an annulus, this is the equation when if we treat the annulus like this as a annulus, and this one if the temperature profile if we treat it the annulus as a parallel plate, yeah, which is n equal to the Brinkman number k, which is the ratio, and also 1 over k squared. Okay, I would show you what is the, for example, let's have an example with a number. Okay, so for example, we have a inner cylinder which is stationary, and in the outer cylinder which is moving with angular velocity of omega. Okay, so and then we can substitute the mu, let's say the 92.3 centipoise, rho, for example, this is the maybe oil or something, yeah, it's quite thick, thicker than water. And then this is thermal conductivity. This is the TB. Let's say the TB is 100 degrees Celsius. The TO is 700 degrees Celsius. This is the radius, the outer radius, for example, the R, yeah. And then K is the ratio between the inner one to the outer one, yeah, the kappa, yeah, K or kappa. So, and then the omega is the angular velocity, yeah, kecepatan sudut. And then the angular velocity is also very fast. It's very fast, yeah. So if you can imagine, this is 7,980 radius per minute, which is it's been really fast, yeah. And of course, it's very understandable because of the changing of spinning, the fluid would be also heated up. Okay, so this is a modeling or a calculation that has been calculated before. So if the K or the radius between the outer cylinder and then the inner cylinder, yeah, for example, so if this is the kappa R, and this is the R, let's say. And if the K is 0.99, which is very small, then if we want to model it with the plate or if we want to model it with the annulus, they have quite similar temperature profiles. Okay, so the temperature profile from 0.99 to 1 on the fluid, it would be looks like this one. Okay, so this is the this is again dimensionless number, so it's easier to see. So this is a temperature, this is a TB minus T0. So you can just substitute, the TB is 70, this is so the TB is 100, TO is the T0 is 70 degrees Celsius here in the previous case. So you can get your temperature profile of the fluid inside both sides. Okay, and then this is zeta or C, yeah. This one, the C, is actually R over R. So this tells you that kappa, which is actually this one is kappa, yeah, over here. So this is actually when the kappa is 0.99, and then this one is the fluid that would be here. So both simulation shows that this annulus can be treated like a plate. However, if you change the kappa, if for example you make it a smaller radius, it will change the direction. Okay, let's say if we find that the kappa is 0.5, let's say we have a inner cylinder like this, yeah, and then the outer cylinder like this one. So it's really like a very small one and also bigger one, and the kappa is 0.5, yeah. Kappa is 0.5. So this equation doesn't do very well. So it would be looks like this one. Yeah, the annulus would looks like this one. This is the profile. Well, using the plate, it's using that one. So your velocity profile, sorry, for your temperature profile from For example, this is the kappa R, and this is the R. It would be yeah, a little bit quite different, yeah, especially around this area. So around this area, it will be quite different. Okay, so that's why we like to use because the solution is quite similar for type of problem, so we can use it using dimensionless number. So we can apply it using yeah, to this graph, yeah, or to that one. Okay, and then this one is an example of ujian, yeah, I think 2 years ago. Sorry, I only got it in Indonesian. So for example, we have, but I think you should be able to do that. Yeah? So we have a dua plat miring, like this one. And then there's a fluid, stationary fluid, and the temperature TA less than TB. You can use the zero coordinate. Yeah, so this is the zero coordinate. And then using equation of energy, you can use the differential equation that shows the temperature profile on the steady. So this tells you this is steady. The temperature to tell you about the temperature profiles, and then and also temperature rata-rata, yeah, the average temperature. So anyway, this tells you the equation of energy would be looks like this in a Cartesian coordinate, yeah, the Cartesian coordinate. And then the fluid is stationary, so you end up with this one is 0, and you end up this one is k dou square t over dou x square. And then you get the boundary condition when x equal to 0, t equal to tb, when x equal to b, t equal to ta. Okay, and then yeah, you can just do the integration and then get the c, and then get the c1 and get the c2, and then you get the profile. Yeah, again the profile. Or if you want to make it into dimensionless number, you can make it t minus tb minus divide both sides with over here, so you can get the x equal to xb, yeah, which is very yeah, I think it's understandable because it is steady. Okay, I think there would be much variation about this equation of energy. We can focus on type or difference problems, yeah, just to make sure you're used to do the equations. Okay, so maybe for now, any questions? Hello? No? All right, it's not really interactive with the internet. Also, maybe if you're in the campus, internet also like goes on, yeah. So I think we can conclude it here for today. We can continue next week with still about dimensionless number of equation and energy, and also we're still checking the and then I think need to check when is the exam, but hopefully sometimes next week there would be quiz, maybe on Friday, yeah, after we do number of problems on Wednesday. All right, even the assignment is not submitted, but I hope you can do it by yourself and then check it with your friends, yeah, and then check everything's right. Okay, there is any question? No? Okay then. All right, I think I need to conclude the lecture. I'm sorry for that. Hopefully I will be getting better soon, yeah, with the little bit coughing. Okay, thank you, and then I'll see you again next week. Bye-bye.